Hi, hello everyone, and welcome to this video. And this time I promise that we're going to work on attenuation. So this is where we left off last time. And just quickly, what is attenuation? Well, it's basically full of some value, which is usually, let's say, for light. It's the lightness as it is, and as it goes into distance, it actually falls off. So you can see here definition in physics, blah blah blah. It's gradual loss of flux intensity through a medium. Our medium, I guess, is air. I don't know. We're just going to model it like this. But basically, it's a fall off, and we can. So how this attenuation is going to look like? Well, let's see. So basically, if let's say that we have some light here, and here we have this cube, right? And this light is going here. It kind of falls off, the value of the light falls off with the distance, right? The greater the distance, the less light the cube is going to receive. So we can usually model it maybe, let's say here, right? We're going to say, okay, our light here is 1, and let's say that this axis is d for distance. And as distance increases, right, distance goes into this direction, the light the value of the light, and here we say the value of the light, so let's call it lightness, it kind of falls off with distance, right? And we can model it sort of like that. So here I'm using Desmos, which is a pretty neat tool if you need to model just functions. So we can say f of x, and this is our y value, is equal to x. And we're going to say that x is our distance, so we have to remember that. So how do we model out attenuation? So we can say 1 over x, right? We need to reverse it because it's falling down. So it looks like this now, and then the attenuation is usually modeled. We have a quadratic term, so it's modeled as x times x and then times quadratic term. So here we're not seeing anything because I haven't assigned the value for it, and it can be some smaller value. You can see now that the fall off looks sort of like this, but we can also add two another terms. One is linear, and here I actually want this to be really small, and linear a bit smaller, and then we also have constant. So now I'm going to model it quickly. So we can say our constant term plus x, which is our distance, times linear term, and then plus this, and we have some nice function which kinda, right, we're starting here, our light is at constant term 1, and then it falls off, the value falls off over distance, right? If you remember, I mentioned that this is distance, and then the value is falling off. So you can model it sort of like that. And in physics, at least I read, so the attenuation is usually modeled as 1 over some quadratic term, so distance squared, which we have here, and then we also just have some values to further improve the function. So we have here a linear term, and then we have constant term, right? So we can model that real easy in our game. So we're just going to start from the shader, and then we can go to material shader, and here we're going to need more bytes for this, but we can say here, for example, I'm just going to use atten for attenuation, and then we can say constant, or just const, and then we can say attenuation linear. So this is our linear term, and attenuation quadratic for quadratic term. And then since it needs to be aligned to basically vector 4, here we have, let's see, what do we have? Oh, come on, wrong button. So here it's 4 vectors, here it's 4 vectors, here it's 2, so we just need offset of 2 here, and I can inspect both. So just so that we nicely align it in memory. If you remember, I mentioned that it needs to basically be aligned by 4 floats, so 16 bytes. And then we can model that attenuation somewhere over here. So we're going to need distance. So we can just say float f distance. And which distance do we need? Well, we need distance between our light, right? Our light and our cube. Let's say that this is cube, so we need this distance. So we already know that we have light position. So we need, here is formal distance. So we need to pass in light position and then the fragment position as well. And that will give us our distance. Then we can just say atten for attenuation. So here I'm going to reverse a bit later, but here let's just do this. So we have here, where is it? We have point lights I. So first of all we have this constant term, then plus linear term. So we have distance time point lights dot linear term, attenuation linear, exactly. And then finally we have quadratic, so this is plus distance time distance, which is distance squared, and then times I dot quadratic. All right, so maybe I can enlarge this a bit so that it's easier to see, and I could do this as well. So maybe just zoom in a bit. So I mentioned that we just now have to do this 1 over, right, and this is it. Okay, so basically, just to recap, the function looks basically like this. We have distance, right? So we say our attenuation is 1 over constant term, then we have plus distance times linear term, and then plus distance squared, or distance time quadratic term. And this is q, sort of. All right. And then we just have to multiply it here, and that's it. All right, that's almost it. So we just now have to paste it in our lights. And here we're going to have to do the following. So this, because we need to expand it over our original size, we're just going to change everywhere to see the float 3 times 4 here as well. And then we can also model that attenuation somewhere over here. So we have attenuation constant term, it's of type float, and for constant I'll use 0.5. You can model it in Desmos and see how it will look like. For linear, usually some smaller value is good, so 0.2 maybe, and then for linear, and then for quadratic, even smaller value, 0.8. And then we can just paste them in here. So we have a light, and here we have constant, and then another vector for light dot linear, and then we can just paste 0 and 0 here. We don't care about that. And with all of that, this should actually kind of work. Let's see if it works. Where light was never mutated. Consider changing it to light. Okay, I can do that. I can do that. Where is... Okay, now lights are kind of dim. Here we'll have a bit of artifacts, but actually it kind of works. So what I'm going to do next is, in our coordinator, I just want to switch our directional light to defaults, and here we can probably play with this attenuation. So we can say point lights, let's just say here, constant, and let's just pass it to really high values just to see if it works. It should. Let's see. No. The greater the value, the less light there is. So if I paste it to 0.1, it should actually be, if you model it, if I pass in for our constant term 10, you can see that value drops. But if I pass in, let's say 0.1, you can see that value is considerably higher. So higher value here will result in actually less light. Okay, right, let's then do this. Let's just say 0.1 for constant. So our last light, let's see what it's going to be. It should be really bright now, and it kinda is. That's this one. It kinda is. Okay, we figured that one out, so let's see what we're going to do further. Actually, let's spend more time here because I have values that actually look nice, which is what I had when I was preparing the video. So here I use 0.3, 0.1, and then 0.04. So I think this will look probably a bit nicer. Yeah, it kind of looks nicer. Alright, so basically that's it regarding attenuation. It's just basically a fall off from light, right? As the light travels in a distance, basically we just model some kind of fall off, right? Here it might be 10, here the value over some distance, let's say that it traveled 2 meters or whatever, and light value now is maybe 2, right? So basically that's what we modeled here. And now what I want to do is actually just some input so that we can prepare our game and play it, and the next time we're going to actually do specular lights. But let's just do some input because it's sort of, we don't even have a gameplay, so I just want to cover that. And here I'm just going to create input, and then new class. I'm just going to call it input manager. And here we're going to need game controller, I think. So I have input manager. So how am I going to model it? Well, basically the main part is just going to be well, we're just going to use keyboard, and then if key is pressed, we're going to check it. If it's pressed, we're going to return true. If not, we're going to return false. Very simple. So we're going to have key code in our dictionary, and then bool, which just says, okay, this key is pressed, it's not pressed. That's it. So in our constructor, so here it gets interesting. We can use this notification center, and then use default, and then add observer. So what do we want to observe? Well, we want to observe, let's see, we want to use this overload. So there are multiple overloads, so I'm just going to remove this because this suggestion is kind of bad. So we're going to observe if keyboard did connect. So that doesn't mean that you have to plug your keyboard. It's going to return event which says, okay, we have found a keyboard, we don't care about this, and we don't care about this queue either. So it's a callback. I'm just going to enlarge this, which takes in basically notification. So this is our in parameter that we get. So code here, and this is a parameter of a callback. So we're going to need keyboard, and we get it from this notification, that object, and then we have to cast it. So yeah, you can check in the documentation of a Swift and make for that, because I don't expect that no one will probably know this by heart. But we have a keyboard now, so on our keyboard we can check keyboard input, and we call key change handler. And this is also a callback, which has a lot of parameters. So first one is keyboard, then it has key code, which we care about, and then it has pressed. And then in this, we can just set our dictionary. So key pressed. We save that key code. If you remember, we had this key code. So this key code is this is also the same type. And then we can just say if it's pressed, and this is just a boolean. Okay, we're done here almost, and then we can just say is key pressed. We're going to check key code, which is of type say key code, blah blah. Then we return some bool, and then we can say return key pressed, and then we just pass in that key code, and this should return us true or false. And if key code is not present, we can just say false. We can just say false if there is no key at all in dictionary. That means that it was obviously not pressed. So here we're almost done here. Now we just have to go to our pedal. And here I have a couple of things that I have to model. First of all, I'm just going to get rid of this rotation stuff. Angle and here rotations, if we don't care about that. So how do I want to do this? Should I call it in update or draw? Well, I guess I could create a draw functions just so that we have this here. So we're going to need, what we're going to need is that input manager. So this can be private let input manager. Then I call it input manager. My bad. Okay, in our pedal we have input manager, we have to pass it in. So now how are we going to model this? Actually, what I want to have is just some public var, and it's going to say player 1. So our game is going to be for 2 players, and then we're going to have some pedal speed, which we're going to model with float, and I use this value for default. Further in update, we can just say direction y, type float, and by default it's not moving anywhere, right? So if we are player 1, and then we can say if input manager keys key pressed, and then we can just say our player 1 is going to use WEASD keys, so we can say direction 1. So this is up, so direction 1 is up. And then we can also check else if input manager is key pressed, and for down we're just going to use S, direction Y -1, and then else. So else if this is player 2. So here I can just copy paste this. Here I'm just going to say up arrow and then down arrow. And we can just change our position.y plus equals direction.y, right? Then times pedal speed. And now we just want to clamp it. So well, let's actually test this. We can test this. So I just have to create input manager. I can do it somewhere over here. Input manager. Since it has an empty constructor, I can just create it here. And then in our pedal, we just need to paste it in. Okay, let's try it. Let's give it a shot. All right. If I press anything, nothing happens because I haven't called update on our pedals. So let's say pedal 1.update, pedal 2.update, and I'm just going to set pedal 1 to be player 1. True, and pedal 2 player 1 is false. So theoretically, let's see, it works. Okay, cool. One more thing to do. just in our pedals, if I could find them, here. So I just want to clamp this value so that it doesn't go out of screen bounds. You can probably do this a bit better than I'm just going to hard code it, but it is what it is. So if our position is above 5, we're just going to set it to 5. Else if position.y is less than -5, I'm just going to set position.y is -5. So that means we're going to clamp it. And I think that's good enough, right? So it's clamped here, and that's good enough of area to work with. Okay, that's it for this video. Hopefully you enjoyed it. It's a bit shorter, not much to do. So the next time we're going to cover specular lights. After that I would like to maybe do some gameplay and shadows. And I would like also to do split screen, and then we're finished with this series. So maybe a couple of more videos to go. So if you enjoyed it, please like, subscribe, maybe leave a comment, and until next time.